Thanks a lot for inviting me to speak at the seminar. It's nice to get the chance. So it's what I'm talking about is a collection of very elementary techniques. So in contrast to Christine's talk, where we're hearing about, things we have to do a lot of serious work on the analysis side to sort of exploit these variants of these classical harmonic map methods. In our case, sort of the analysis is all trivial, and the miracle is that you get anything out of it at all. Okay. So let me just give you a sense of where my motivation was coming from for looking at this in the first place. So when I was doing my PhD, I was very interested in using sort of PDE methods and then some, energy concentration phenomena to produce minimals of manifolds. So there are all these cases where you can take sort of limits of some nice, well-behaved geometric PDEs and get minimals of manifolds coming out. And sort of some simple cases of this that have been understood for a while is that if we're on in the codimension 1 case, on a given manifold, there are lots of variational problems for real or circle-valued maps whose solutions have to collapse as some parameter varies to minimal hypersurfaces. So sort of two of the classical examples are if we have, say, real-valued solutions of some, these are called Allen-Kahn equations, so these are critical points of some energy functional, where you have a Dirichlet term plus some term that's trying to pull your function to, say, plus or minus 1. Then as you take this parameter here, getting very, very small, right, you're going to, in the limit, look like some characteristic function or, something taking values in plus or minus 1. And in fact, the level sets have to all sort of collapse along some minimal hypersurface, it turns out, in the limit. And this has been exploited in various ways in recent years. And then sort of another case, which just sort of falls out of the co-area formula, is that if you take a homotopy class of S1 valued maps and then minimize the LP norm of the gradient, this is sort of a well-behaved problem, if P is strictly bigger than 1. And as you take the limit as P goes down to 1, it's sort of not hard to convince yourself from the co-area formula that all of the fibers of these maps have to collapse along an area minimizing representative of the associated homology class, right? So it's easy to find sort of natural geometric PDEs with this, behavior of collapsing down to minimal hypersurfaces. And this has been exploited a lot, sort of analytically to produce minimal hypersurfaces. But a question that was always sort of at the back of my mind from early on in my PhD was, to what extent does the geometry of these fibers, in some average sense, I mean, you don't expect it for every fiber, resemble that of the limiting minimal hypersurfaces before passing to the limit? So is there any, geometric sense in which these things look like minimal hypersurfaces before passing to these limits where they actually do, coincide with them? So in particular, if you can indeed conclude that they resemble minimal hypersurfaces, can you then, look at the many applications of minimal hypersurfaces to geometry and topology and physics, and maybe take a different approach and get some different information by looking at level sets of some natural geometric PDEs. So that's the starting point. All right, and so what's one of our favorite applications of minimal hypersurfaces is to scalar curvature. Okay, so a natural test case is to ask whether we can sort of look at level sets of some geometric PDEs and get some kind of information about scalar curvature from them. Okay, so maybe I don't need to for this audience, but I'll just quickly remind you about use of minimal hypersurfaces for scalar curvature. Okay, so suppose we have some closed-oriented manifold of dimension at least 3, and let's suppose we have some integer homology class. It's important that we're integer coefficients so that we get two-sided things coming out. Okay, so by classic results in GMT up to the 1970s, we know that any of these non-zero homology classes is going to be represented by some smooth two-sided area minimizing hypersurface if we're in dimension less than or equal to 7, and then with a small singular set if our manifold has dimension 8 or higher. All right, so of course, as a minimal hypersurface, its mean curvature vanishes. But more importantly, we can check the second variation formula and see that we have to be stable, right? And so the standard form of this stability is just that, if we move with speed phi in the normal direction, then we have that the Dirichlet energy of phi along our hypersurface minus second fundamental form squared plus Ricci in the normal direction integrating against phi squared is non-negative. Okay, that's a classic computation. All right, so on its face, this tells us that stable minimal hypersurfaces should tell us something about Ricci curvature. And of course they do. So I mean, a sort of elementary example is that you can use minimal hypersurfaces, stable ones, right, to prove that if you have positive Ricci, then the codimension 1 integer homology has to vanish, right? Because if you just look at this formula, well, if you have positive Ricci and you take phi to be a constant function, then clearly you're going to get a contradiction here, right? So if you don't have any stable minimal hypersurfaces in positive Ricci. And of course, there are more sophisticated applications of this to three manifolds of positive Ricci curvature, for instance, by Shane and Yao. Okay. But this kind of beautiful observation of Shane and Yao in the 70s was that just using the Gauss equation, you can rewrite this Ricci term in terms of the ambient scalar, so there's the scalar of our ambient manifold, minus the intrinsic scalar curvature for the induced metric on the minimal hypersurface, and then you cost a little bit of second fundamental form squared. But if you plug this back in, right, you see that you have the stability inequality becomes this. So now, positive scalar curvature clearly isn't going to rule out having stable minimal hypersurfaces. You know, the simplest example is your S2 and S2 cross S1, right? But it's going to somehow constrain their intrinsic geometry, right? So that's the big observation of Shane and Yao in the 70s. So it's particularly simple to see in the three-manifold case. So if we're in on a three-manifold, then flowing with speed 1 and just applying Gauss-Bonnet to that intrinsic curvature integral, then we have that 2 pi times the Euler characteristic is bounded below by this integral of second fundamental form squared plus ambient scalar curvature. Okay, so immediately we see that if we have positive scalar curvature in the ambient manifold, and we're calling this surface is oriented, right, it has to be a sphere or a collection of two spheres, right? If it's disconnected, each one satisfies this separately, right? So in the application, right, we see that the degree 2 homology with integer coefficients has to be generated by embedded two spheres, for instance. Okay. And so, this, for instance, implies that T3 admits no metric at positive scalar curvature, right? Because on T3, any two-dimensional homology class is going to be, dual to some two form represented by a wedge of two cohomologically non-trivial one forms. But that means these pull back to non-trivial one forms in your surface. So you can't be a two-sphere. Okay. So this is classic stuff from the 70s. All right, and variants of these ideas in the asymptotically flat setting give rise to the first proof of the Riemannian positive mass theorem by a contradiction. Okay, and we'll come back to the positive mass theorem later in the talk. Okay, so the talk's mostly going to be in 3 dimensions, but just I should at least mention higher dimensions. So if your dimension less than or equal to 7, or 8 with some work by some work of Nat Smale, the same observations with a little more sophisticated machinery can be used to show that if you have a closed oriented manifold of positive scalar curvature, then the codimension 1 homology is generated by embedded hypersurfaces of positive Yamabe type. So they all admit metrics, in fact, even conformally from the induced metric with positive scalar curvature. Again, that just falls out of this stability condition. Okay, and so in particular, this allows them with this inductive argument to prove non-existence of positive scalar curvature on Tn when n is less than or equal to 7 or 8. Okay, and of course, this was proved in all dimensions by Gromov-Lawson via Dirac operator methods. Okay. So I should just mention that recently Shane and Yao have extended some of these ideas to dimension higher than 8 or 9, but there the argument's more complicated because somehow you really have to allow for the possibility that your minimizing hypersurfaces have singularities and somehow work through them. Okay. So it's, of course, a famous open problem in GMT, whether area minimizing hypersurfaces are smooth for generic metrics in dimension higher than 9. If that's true, so it's known in dimension 8, so you can have singularities in these minimizing hypersurfaces for specific metrics, but it's known by Nat Smale that you can perturb them away. Okay, so maybe I should just mention here, there's a grad student of Fernando Cotamarquez, Jihan Wang, who's actually made some interesting progress recently on extending some of these generic regularity ideas to higher dimensions. So it's far from sort of giving you everything you would like here, but there's maybe some recent hope for getting generic regularity results in higher dimension. So if you can do that, then that would greatly improve life for minimal hypersurface techniques. Anyway, so returning to this question about level sets. So, testing out our initial question in the positive scalar curvature world, you can ask the following. So for a stable solution of the Allen-Kahn equations, say, or for one of these p-harmonic S1 valued maps, are some of the level sets, well, in high dimension, you would want to ask if they're a positive Yamabe type. But in dimension 3, we have the more modest question, should some of the level sets be, say, unions of two spheres, or at least have two sphere components, okay? So in dimension 3, maybe I'll point out that the Allen-Kahn version of this question, we know from work of Chodash and Mantoulidis from the last, 5 or 6 years ago now, that you do have not just some weak convergence, but really a strong strong convergence of these level sets to your minimal hypersurface. So in fact, in that case, you at least know that these must have the same topology as epsilon gets sufficiently small. Okay, so there's reason to think that something like this might be true. Okay, so but let's focus on the simplest PDE we can look at first. So if we take either the epsilon goes to infinity limit of this Allen-Kahn problem, or the p equals 2k, so the p energy minimizing maps, then we come to a very simple thing, which is just harmonic maps to S1. Okay, or if you'd like, harmonic functions for the real valued case. And these are essentially the same thing. So just to remind you about harmonic S1 valued maps. So when you're first learning harmonic maps, these are sort of, I think, one of the first examples you see because they're the analysis is completely trivial. So let's suppose you have a closed oriented n-dimensional manifold, and recall, like by point graduality, that we have this isomorphism between the degree 1 cohomology with integer coefficients, the homotopy classes of maps to S1 with the obvious group structure, and the n-1 homology with integer coefficients. Okay. And to write the isomorphism in most directions is easy to see, right? So if we have a homotopy class of S1 valued maps, pick your favorite smooth representative, take a generic level set, and that will land you in the corresponding homology class. And okay, so for instance, on the cohomology side, right, take again your favorite smooth representative of this class, take the sort of associated gradient 1 form given by just pulling back the obvious 1 form from S1, and then that'll give you a de Rham cohomology class. And that map's going to be well-defined and injective, importantly, so it gives us a natural identification of the degree 1 cohomology of integer coefficients with a lattice inside the de Rham cohomology of degree 1. So that's in particular an important point, is that for the degree 1 cohomology with integer coefficients, or the codimension 1 homology, there's no torsion there, right? These are free, torsion free. Okay. All right, and so with these identifications in mind, it's not hard to see that the problem of minimizing Dirichlet energy in the homotopy class is equivalent to just minimizing the L2 norm of this 1 form, this gradient 1 form of the associated de Rham cohomology class. Okay, so in particular, finding a harmonic map in this homotopy class is essentially the same as just finding a harmonic 1 form in this this de Rham cohomology class, right? Okay, so in particular, Hodge theory gives an energy minimizing representative whose gradient 1 form is harmonic. Okay, and of course we could use Eel-Sampson machinery if we wanted here, but we really don't have to. This is all linear PDE. Okay. All right. Okay. So in particular, pick your favorite codimension 1 homology class, the integer coefficients. Then there's going to be some harmonic map, which is unique up to obvious symmetries, whose fibers represent this homology class. Okay. So returning to our original question, we want to understand to what extent scalar curvature says something about the geometry of the fibers and vice versa. Okay. All right. So I was playing around with this question a little bit this summer between finishing my dissertation and starting my postdoc, and came up with the following thing. So if you have a closed oriented three-manifold, and you have a non-constant harmonic map to S1, whose fibers are given by sigma t, say, then if you look at the average of the Euler characteristic times 2 pi, this is bounded below by, well, there are different ways of writing this. One is you can say the average of the over the fibers, or the integral of the fibers of this this quantity here, so half of this sort of Hessian squared term plus the ambient scalar curvature. All right. So maybe you can note this looks like an averaged form of the Schoen-Yau inequality for stable minimal surfaces in three-manifolds. Okay. And of course, you will have critical points in general. So you can't just sort of write these quantities down and, be happy with them initially. So there's a little bit of work in checking that these things actually make sense. You can actually say this rigorously, right? So let's see. So the simple idea is basically you want to take the Bachner formula, but instead of looking at Laplacian of half the norm of h squared, the natural thing to look at is Laplacian of half the norm of h, because then you get something coming out where your right-hand side is curvature terms with a weight norm h, which looks nice for applying the co-area formula, right? And then there's sort of a nice Gauss equation trick a la Schoen-Yau to treat the Ricci term in the Bachner formula. So it's a very very elementary idea. Okay, so to make it a little rigorous, right? So suppose this is our gradient harmonic 1 form. We'd like to take Laplacian of norm h, but okay, that's not going to be quite smooth. So maybe we regularize a little bit. This is sort of a standard trick, right? So we replace it with, say, norm h squared plus delta to the square root. Okay, and the Bachner identity gives us the following. This is just, again, the standard Bachner identity for harmonic forms. Okay, so now we're just going to copy Shane and Yao's Gauss equation trick, and recognizing that this Ricci HH term is really a norm h squared times Ricci in the normal direction to these level sets, assuming, for instance, for the moment that we're at a regular level set, then we can rewrite this Ricci HH as half norm h squared, ambient scalar minus intrinsic scalar of our level set, plus mean curvature squared, that's going to be a non-vanishing term now, minus second fundamental form squared. All right. But then, we can, of course, write down what second fundamental form and mean curvature are explicitly in terms of just the Hessian of this S1 valued map. And we arrived at this. Okay, so this is just computations. Okay. All right, so now we're going to play around with this a little more. And so rewriting our Bachner formula, we arrive at the following. Okay, so now we have this Hessian squared term plus ambient scalar minus intrinsic scalar. Okay, so now we have to be a little bit careful. So this holds along regular level sets. We want to somehow integrate over all fibers, right? So let's be careful. So let's divide our target circle into two sets. One is going to be a large compact set containing all the regular values. And then we're going to be left with a very small open set containing the critical points. Okay, which we can do by Sart's theorem, right? Okay, so divide it into two such sets. We integrate over the regular value set, and we apply our Gauss equation trick there and use the co-area formula. On the remaining piece, we're just going to use the standard Bachner formula, right? Because we're not allowed to use Gauss equation through these critical points. Okay. All right. So all we've done there is co-area formula. All right, and then finally, right? So we can let's see. We take delta going to 0. We get the following identity. This is now for our norm h term. Okay, so we get that integrating over this nice large set of containing the regular values, we have 2 pi times the Euler characteristic is bounded below by the thing we want, minus just this L infinity of Ricci times the integral of area of the fibers over U. Right? So we just use co-area formula here. But the point is the map sending point in S1 to the area of the associated fiber is integrable. And by Sart's theorem, we can take the measure this U as small as we want. Okay, so we can take that measure going to 0, and we get the desired identity. Okay. Questions about the tricks there? Awesome. Okay, so we have some formula. This wouldn't be interesting unless we could actually do something with it. So what can we do with it? So suppose now that we're a closed-oriented three-manifold, and let's assume that we have no non-separating spheres. Okay, so we're not saying that pi 2 is 0, we're just saying that there's no sphere that's homologically non-trivial. Okay, this is true, for instance, if we're in T3. Okay, so now let's take this harmonic S1 valued map, assuming we have some non-trivial cohomology class in degree 1. It's not hard to see that then each component of a regular level set has to be homologically non-trivial. Okay, so for instance, you can see this by pairing with the Hodge dual of our R1 form H, right, our gradient form, because that has to be a positive integral. And since our form is harmonic, that has to be a closed 2 form. Okay. All right, so in particular, if we have no homologically non-trivial 2 spheres, and each component of our level set is homologically non-trivial, then this tells the total Euler characteristic of our fibers is going to be non-positive, right, for every regular value. Okay, so we just apply this in this cute identity we had before, and we see that this quantity here is non-positive for any harmonic map. Okay. All right, so in particular, this gives you the simple proof just via harmonic 1 forms that any three-manifold of positive scalar curvature and non-trivial codimension 1 homology has to have non-separating 2 spheres. Okay, so for instance, this rules out positive scalar curvature on T3. Importantly, it doesn't, give you the full strength of the Shane-Yao result at all, right? So in particular, it doesn't tell you that you have no positive scalar curvature on, say, T3 connects MS2 cross S1. So to sort of apply these methods to get more in that setting, we'll come to that in a minute. Okay. All right. So what else can you do with this? So by refining the argument a little more, we get a somewhat stronger quantitative statement that you don't get from the minimal surface methods. Okay, so let's define this notion of Thurston norm, which you can imagine was defined by Thurston. So given some codimension 1 homology class in this oriented three-manifold, we want to understand something like the minimum genus needed to represent a homology class. And it turns out that the right notion, if you want something that behaves like a norm, is for any representative sigma with, say, connected components S1 through Sm, if it's a sphere, you throw it out. And if it's, say, has positive genus, then you add up its the absolute value of its Euler characteristic. Okay, so it's kind of like the absolute value of the total Euler characteristic of this representative when you've just thrown out the sphere components. Okay. And the idea is the Thurston norm is to take the minimum over all representatives of this quantity. All right, so if M contains no non-separating spheres, and we have a harmonic S1 valued map dual to this given homology class, and it follows immediately from the arguments we had before, right, that minus the total Euler characteristic of that fiber is bounded below by the Thurston norm, just because it has no two-sphere components. All right, so we can apply the little identity again. And now we're using the form where we're not doing the co-area formula, but just adding this norm du weight and integrating over the whole manifold. Then we see that 2 pi times the Thurston norm is bounded from above by this quantity. And then just with little Cauchy-Schwarz and throwing out our Hessian term, we see that it's bounded above by half the L2 norm of the negative part of the scalar curvature times the L2 norm of this du. Okay. And moreover, equality forces the Hessian to vanish and the scalar curvature to be constant. Okay. All right, so why is that nice? Well, this L2 norm of du, remember du is the energy minimizing representative of its homotopy class. So really this is sort of a canonical norm on cohomology called the harmonic norm, right? So for any, if you like codimension 1 homology class or equivalent to degree 1 cohomology class, right, we just look at the norm of the L2 norm of the harmonic representative, that's called the harmonic norm. And then we get the following. So if we have a closed oriented three-manifold with no non-separating two spheres, then for any non-zero homology class, we have that this 4 pi times the Thurston norm is bounded above by negative part of the scalar curvature in L2 times just this harmonic norm of the associated cohomology class. And moreover, equality implies that M is covered isometrically by a cylinder over some flatter hyperbolic surface. Okay. Great. So there's been a lot of interest over the years, more in recent years, in relationships between Thurston norm and harmonic norm. And what's fun is that, in fact, if we add the assumption that the manifold is irreducible, okay, so now there are no pi 2, right? And the same estimate expressed in terms of the dual norm in the degree 2 cohomology was given by Kronheim and Morovka back in 95, where they're then using machinery from Seiberg-Witten theory and some kind of very deep results from contact and symplectic geometry. So it's very surprising that you get sort of the same sharp estimates coming from these two different things. It's not entirely clear what the relationship is between the Seiberg-Witten method and these just kind of elementary harmonic form techniques. Okay. All right, so what do you get if you use minimal surfaces? You can say something similar. In the minimal surface case, what you see is that 4 pi times the Thurston norm is bounded from above by the L infinity norm of the negative part of the scalar curvature times the least area norm of this homology class. Whereas you can imagine least area norm just means take the area of the area minimizing representative. Okay, so for the minimal hypersurface case, what you learn is that you have to have a lot of negative scalar curvature along your minimal hypersurface, so in particular in an L infinity sense, whereas with either these sort of Seiberg-Witten or harmonic form games, you see that you have to have a lot of negative scalar curvature in an L2 sense if you need a lot of genus to represent your homology class. Okay. All right, so I mentioned before, one sort of drawback of these techniques is that they don't play well with non-separating two spheres. If we have two sphere components in these fibers, then we start to run into problems. Okay, so as I said, this is good enough for ruling out, this previous identity is good enough for ruling out positive scalar curvature metrics on the 3 torus, but not on manifolds like T3 connects some S2 cross S1. Okay, so in particular, if you want to prove, say, positive mass in dimension 3 by looking at, compact manifolds, you need to be able to rule out PSC on, say, T3 connects some any 3 manifold. Okay. So to illustrate on T3 connects some S2 cross S1, you can consider some degree 1 cohomology class given by pullback from the degree 1 map. Okay, so take, consider the, map into the T3 factor, take your favorite degree, one form class there. Okay, so maybe I'll actually try to make a little picture on the board here. Right, so what could go wrong? So let's see, so here's your T3, and then let's say you're connect summing an S2 cross S1. Okay. So you're taking the homology class. By the way, is this visible? Okay. So maybe
somewhat. It's hard to see a little.
Okay, maybe I'll make it a little bigger.
Is there a darker color?
I don't think so. So I'll just, let's see, I'll just be brief and then back you. So the point is, let's say you have a class here, which has to be represented by a torus, right? You can't have this class represented, only by S2s. The problem is that if you're taking your harmonic representative, as you come around sort of this piece, you can have, a representative which is a torus piece here, but then picks up an extra S2 in the S2 cross S1 factor, such that their total, the homology class they represent together is still the original one. Okay. So that's sort of, something that seems unavoidable. Okay. So how can we get around this issue for applications? So this was some work with, let's see. So in particular, it can turn out that the average Euler characteristic is positive, even though this homology class can't be represented just by unions of two spheres. Okay, and moreover, and this is kind of a crucial point, is we can't separate these level sets into their components and analyze them separately, because unlike being a stable minimal hypersurface, the condition of being a level set, of being one of these harmonic S1 valued maps, is a non-local condition. Of course, if you're talking about area minimizing hypersurfaces, that's also non-local and is maybe the closer analog to being a level set of one of these maps. But anyway, that's sort of the drawback. For the minimal surfaces, we can separate these stable guys into their components and really say we have to be represented by a union of two. All right, so if we want to apply these harmonic form methods on manifolds that do have non-separating S2s, so say something connects some S2 cross S1, then it's helpful to cut out some generating set of non-separating minimal two spheres. Okay, so there's this idea that we introduced in a paper with Hugh Bray. Okay, so in that case, it's useful to then have the extension of these techniques to manifolds with boundary, right, after we've cut some things out. And that turns out to be relatively straightforward. So if we have a manifold with boundary, now if we look at the homotopy classes of S1 valued maps, these are naturally isomorphic to the degree 1 cohomology still, which is now isomorphic by Poincare-Lefschetz duality to the relative degree 2 homology, so the degree 2 homology relative boundary. Okay, and if we want to take an energy minimizing representative of this class, it's again just going to be given by one of these harmonic 1 forms, but now with some Neumann boundary condition, right? It's the condition of being absolutely minimizing without boundary conditions. All right. Okay, so we had the following extension with Hugh Bray of the identity to manifolds with boundary. In the case where we again have this harmonic guy with a homogeneous Neumann condition. And unsurprisingly, right, what do we pick up when we add boundary? Just some mean curvature on the boundary. Right, so that's unsurprising. All right, and let's see, there's something in chat here. Oh, I see, it's a message from Bernard. Oh, well, too late. Okay, so as an application, we're able to extend this Kronheimer-Moravka thing to arbitrary closed-oriented three manifolds. Okay, so the idea there, maybe I'll be brief. So first of all, by results of Meeks and Yao, this is kind of the key point. We can find a disjoint collection of embedded minimal two spheres, which generate all of sort of the non-separating spheres in homology. So all the portion of the homology that can be represented by two spheres, we can find, a collection of disjoint minimal representatives such that we can get all of it by their sums. Okay. And so we can cut along these to get some manifold with 2 times the number of spheres boundary components. Right. So for each such 2 sphere, we just cut and we see 2 boundary components there now. And then the idea is to just apply the formula with boundary on that manifold of boundary, and then we're able to somehow relate the relevant norms back to the original in the closed manifold. Okay. But somehow the key takeaway is just this trick of cutting along the minimal two spheres. Okay. All right. So, of course, once you've seen the T3 thing, it's natural to ask about the next application that came for the minimal surface techniques, which is the positivity of the ADM mass. And so this was work with Bray, Cazares, and Khoury. So we're able to extend these techniques to the asymptotically flat setting. All right, so just to remind you, we're going to be thinking about one end of an asymptotically flat three-manifold. So this is just going to be R3 minus some collection of balls, and it can be arranged by results in minimal surface theory so we're cutting along some minimal boundary. Okay, so for the purposes of understanding positive mass and asymptotically flat guys, it's enough to pretend that we just have a topological R3 minus some balls, where those balls are the boundary spheres there are minimal. Okay. Okay, and so I work with Bartnik and various other people over the years on harmonic coordinates. We can always find some harmonic map from M into R3, so if you like a collection of three harmonic coordinate functions, which defines an asymptotically flat coordinate system sufficiently far out, right? So they won't be coordinates everywhere, but if you go out to infinity, there'll be coordinates satisfying some suitable decay conditions. And on this minimal boundary, we can moreover impose, say, some homogeneous Neumann condition. Okay. Corresponding to the condition that pops out naturally when you're doing minimization problems in the compact setting. Okay. All right, so the ADM mass, I'm guessing for this audience, you guys are familiar with it, but right, we know that if we're in an asymptotically flat three-manifold, then we're sort of Euclidean to leading order at infinity. So the ADM mass is, some natural measure of the next order behavior, how close you are to being Euclidean. Okay, and of course, it really pops out of notions of energy and general relativity. Okay. And so the Riemannian positive mass theorem tells you that if your scalar curvature, which corresponds in the setting to some local energy density in GR, right, is non-negative, then the ADM mass is non-negative, and equality forces you to be isometric to R3. Okay. And of course, this is first proved by Shane and Yao using their minimal surface methods and the contradiction argument. And then there have been various other proofs since then. So probably the most famous of which are Witten's harmonic spinor proof and Huisken and Ilmanen's proof via inverse mean curvature flow, which of course also gives us the Riemannian Penrose inequality. Okay. So once you've seen sort of the torus thing, well, somehow the analog in the asymptotically flat setting of just these, harmonic maps representing the cohomology class in the torus is to look at these harmonic functions. Okay. So, and in doing so, we get to some semi-explicit, explicit is probably a strong word, but a family of sort of nice lower bounds on the ADM mass. Okay, so let M3G be one of these exterior regions representing one end of an asymptotically flat three-manifold. And then we have this harmonic map with Neumann boundary condition defining a coordinate system at infinity. We'll then pick any S2 direction for these coordinates, and the associated harmonic coordinate satisfies the following bound. So the ADM mass for our three-manifold is bounded below by this quantity here, which in particular gives us, something non-negative in the Hessian of this coordinate function plus the ambient scalar curvature. Okay. So in particular, if the scalar curvature is non-negative, then the mass has to be non-negative, and if it's zero, then these coordinate functions have to be, parallel, and we see that we have to be Euclidean. Okay. So under the assumption that harmonic coordinates define global coordinates, so we're actually in something that's topologically R3 and say not too far from being not too far from Euclidean, then this turns out this was actually discovered by the Polish physicist Kijowski in 1980. Okay, so we weren't the first ones to define this formula, although he, I guess, didn't know how to work around critical points, right? So he's assuming these are honest coordinates everywhere. Okay. Which sort of unsurprising that it was seen before, right? Because it's very, very natural. Okay. All right, so the proof idea is, an extension of what we were doing in the compact setting. So again, you're carrying out some Bachner plus Goeria computation, but now you're doing it on some large sort of coordinate cylinder in your manifold. Okay, so its boundary is going to compose into some cylinder region, right? Just the boundary of this cylinder in R3, right? And then your interior boundary corresponding to your minimal two spheres. Right? Okay, and then you get the following computation. So just running the same games, you see that the sort of bulk integral that you want to be, bounded above by your mass is bounded above by the following boundary terms. So you have the integral over the, the values of the coordinate functions taking on this domain of the 2 pi times the Euler characteristic. And then you have some geodesic curvature of the boundary of your level sets. And then this extra boundary term corresponding to the derivative of norm du. Okay. All right. Well, since we have no relative homology, no homology relative to the boundary in degree 2, right? Remember, we're topologically just R3 minus some balls. It's not hard to see that just as all of our level sets had to be homologically non-trivial in the closed setting for the harmonic S1 valued maps, in this case, we can only have one level set, and it's the one meeting the boundary. Okay, or it could be closed, right? So it's either we have one component, and it's either if it meets the boundary. That's right. It has to meet the boundary. Okay. So in particular, the Euler characteristic is at most 1, right? And so we get this bulk integral is bounded from above. Well, our Euler characteristic terms become 4 pi times L, and then minus these extra boundary terms. Okay. But then at the boundary of this coordinate cylinder, you can just relate these boundary terms, it turns out, to this flux integral that defines the ADM mass. Okay, and you get the following. Okay, so you take the limit as L goes to infinity, and you get precisely this bound that we had. Okay, questions about that? All right. Okay, so since then there have been some interesting generalizations. So people have been doing a lot of other things, and so there are various other PMT type problems people study in GR with this. And among these, probably the most interesting, well, there are lots of interesting ones, but an initial striking result was by Sven Hirsch, Dmitry Kazaris, and Marcus Khoury, where they were able to get a space-time version of this. So I won't go into the space-time positive mass theorem, but it's telling you now that you have some analog of having non-negative mass, where now the rigidity case is being a space-like slice of the Minkowski space-time. Okay. All right, and what's interesting here is that instead of using harmonic coordinates, they're now applying these techniques to coordinate functions satisfying a slightly nonlinear equation of the following form. So Laplacian of u plus trace of this 2 tensor that's representing the second fundamental form of your space-like slice in the space-time times the norm of the gradient is 0. All right, and it's just somehow you play with the formulas, and this is something which pops out exactly what you would like it to. One thing that's mildly frustrating about this is that this doesn't have a simple variational characterization, which, if you're like me and like things to be variationally defined, is kind of strange. And I'll note that recently Chai noticed that if you do analogous computations in general for equations of the form Laplacian u is some prescribed function h times norm of Nabla u, you seem to get some similarities with the results that you get by looking at stable mu bubbles in dimension 3. So stable mu bubbles being these stable critical points for 0th order perturbations of the area function, which have been exploited recently very successfully by Gromov and Jin Tianzhu and Chodashin Li and various others. So there's something kind of strange there. All right. So another interesting direction people have looked at is monotonicity formulas. Okay, so by the same Bachner and co-area computation, if instead of integrating over some whole domain, you integrate over the region between 2 level sets that are close together and take the limit, you see the following. So, for instance, you can see that ddt squared of this integral along the level sets of the energy density is going to be given by the same bulk integral we had before along a given level set. Okay, so you can localize these computations along a given level set. And you can build various sort of more interesting monotonicity formulas from this. All right. So in particular, you can apply this to Green's functions as sort of a natural setting to look at. So one of the first results along these lines is by Munteanu and Wang, who were sort of taking inspiration from various monotonicity formulas that Colding had used in his study of manifolds with lower Ricci bound. So he'd been looking at monotonicity formulas precisely along level sets of Green's functions in this setting. And they found some interesting applications, including, for instance, recovering in dimension 3 some instances of what the so-called Dabo-Ono inequality, which tells you that if you have a hyperbolizable manifold with scalar curvature at at most -6, so it's bounded below by the scalar curvature of the hyperbolic guy, then in fact the bottom of the L2 spectrum of the universal cover is bounded from above by the bottom of the L2 spectrum in the hyperbolic case. Okay, so it's interesting, a sort of spectral rigidity result in the negative scalar curvature setting. Okay, and then probably my favorite application as a minimal surface guy is that Chodosh and Lee were able to use, again, some monotonicity formulas along Green's functions, and sort of with some additional subtleties, because now you don't have, in their setting, an a priori lower scalar curvature bound, to prove the stable Bernstein conjecture in R4. So showing that if you have a stable minimal hypersurface in R4, they have to show that it has cubic volume growth, and then use that to deduce by work of Shane-Samaniao that it has to be a flat plane. Okay. So I should mention that just a few days ago, they have a paper on arXiv where they're using mu levels to achieve the same result. And in fact, those methods seem to be maybe a little bit more flexible. So now they have a couple different proofs around of this stable Bernstein theorem, both by Chodosh and Lee. Okay. And finally, you should note that there are some analogies with monotonicity of the Hawking mass along the inverse mean curvature flow. And these have had some application to GR, for instance, by Agostiniani, Mazzieri, and D'Aronzio. Okay. So let me maybe mention a little bit more about that. So first, we can think about the p-harmonic variant of these computations. So at least formally, right? So in the initial motivation, I mentioned one thing to think about is you have these p-harmonic maps to S1, whereas p goes to 1, they collapse to area minimizing hypersurfaces, right? So at least formally, it's not hard to see that these computations play well with p-harmonic functions. Now you don't have a Sar's theorem for these guys a priori, so it's not, there's more analytic work in actually making these rigorous. Okay, but recently, Agostiniani, Mantegazza, Mazzieri, and D'Aronzio were able to make these rigorous sort of in a suitable setting. So for p-harmonic Green's functions on complete asymptotically flat three-manifolds with non-negative scalar curvature and with connected outer minimizing boundary, right? So we're in the setting of the Penrose inequality. So they obtain the following estimate. So the P capacity of this boundary inside this asymptotically flat space is just telling us how much LP norm of the gradient do we need to have a function which is, say, 1 along this boundary and 0 at infinity, right? So what's the least LP norm of the gradient we can have for such a function? That's the P capacity. And I get this upper bound on that by the ADM mass. Now, the P capacity, as P goes to 1, it's again not too hard to see from the coarea formula that's going to converge to the area of the least area minimal hypersurface, right? The least area beyond that horizon, right? So in particular, as P goes to 1, they recover the Riemannian-Penrose inequality. Okay. So it's maybe worth noting that you can actually achieve the same inequalities, the same family, by inverse mean curvature flows. This was done by Xiao a few years before. Let's see. So let me just make a remark here, which is that all of these monotonicity results require those outer minimizing boundaries connected, right? Just as for the inverse mean curvature flow approach. So I would imagine that these would hold with connected boundary as well. But maybe you need to use something more like Bray's work on Penrose inequality to do something with multiple boundary components. Okay, because in particular cases P equals 2 and the limiting P goes to 1 case corresponding to Penrose, are covered by Bray's work for multiple boundary components. Okay. And finally, I'll just mention it's work of Roger Moser from the early 2000s, that in fact you can produce solutions of the inverse mean curvature flow precisely by looking at p-harmonic functions, taking suitable reparameterizations of the level sets, and taking the limit as p goes down to 1. So morally, this proof is sort of equivalent to the Huisken and Ilmanen inverse mean curvature flow approach to Penrose, but it's situating their monotonicity formula in sort of a larger family of monotonicity formulas for these p-harmonic guys. Okay. So finally, I'll just finish with some questions. So the first one, which is kind of a technical one, but given the initial motivation for this, bugs me. So given, say, let's just focus on the scalar valued case. Given some stable critical point of some Allen-Kahn type energy, like the ones I talked about at the beginning, is it necessarily the case that, say, some weighted average of the Euler characteristic of the level sets is positive? So the initial motivation was understanding the extent to which these level sets behave like stable minimal hypersurfaces on average before passing to the limit. But the techniques we have here don't actually work well. It's not sort of not clear. And, I spent some time, 2 or 3 years ago thinking about this, how to exploit stability and those computations simultaneously to get something useful coming out. All right, so maybe a more serious question is whether one can use variants of these ideas to get rigidity results where rigidity favors spherical or hyperbolic geometries. So sort of all the rigidity results I showed favored flat or, some flat cylinder over some surface, right, geometry. And maybe I'll advertise there's some positive work in this direction. Well, first of all, this Montiano-Wang result was a rigidity result for hyperbolic metrics, right? So that's nice. And there's also been announced a proof of the asymptotically hyperbolic positive mass theorem using these methods by Bray, Hirsch, Kazarus, Khoury, and Zhang. So at least in the hyperbolic setting, there seems to be something, maybe in the spherical setting too. Okay. Maybe this, looking at analogs of these mu bubble techniques is the natural thing to investigate there. And finally, back in the summer of 2019, when I was first playing with this, I was initially, sort of naively optimistic that maybe you can say that for a harmonic S1 valued map in higher dimension, you can say something about the Imabe type of the level sets. I spent a while thinking about that, invited various people to think about it with me. We never really got anywhere with it. And it seemed that there might be some genuine obstruction to sort of obvious things you could try to do using these ideas coming from the mean curvature of the fibers. So let's take the more pessimistic approach and ask if you can find an example of a positive scalar curvature 4-manifold with a non-constant harmonic S1 valued map such that none of the fibers have positive Imabe type. So again, sort of the naive tricks we tried to prove that you couldn't do this, there seem to be genuine obstructions, but it's also very hard to actually construct an example where this fails. So that's, if you could do that, I would be interested to see it. But anyway, I think I'll stop there for now. Thanks for having me.